Okay, continue from yesterday. Okay, so this can be like a scratch path. Ah, where are we? Hmm, over here. All right, so we need to talk about half-man coding. So what is our Gemini? Move this closer to Gemini. Okay, so this this man coding give um guarantee uniqueness in the sense that is it possible for the different input to get the same output bit output, aka if hashing collision hashing possible. I don't think so, but let's see. No. Okay, so bijective mapping. Okay, so how do we different input seems to guarantee different output. So we won't have return, we won't have a collision situation. For example, let's say input x give x prime and y give y prime, and y x prime will never be equal to y prime. So it seems like that's what the conclusion is. The one catch. So this is why Huffman coding is designed for no collision, whereas hashing is collision is possible, right? Yeah. Be interesting to implement this in Python or something so that we understand. Okay, so for 1 second, Huffman coding apply on keep output up Huffman coding to, let's say we have ABC and AABBCC. So the second one should give less output, I think, because frequency is more. We got ABC and frequency is 101, makes sense. At B and C, A with that group. and C have double, but the proportion are exactly the same. So what is this in binary, right? Then 0b Python bin string. We have binary Python binary string. So I did 0b 0b. This is output. 175. Can also convert to hex, right? So the original string is, say, ABC Python Huffman coding. I don't want to look at the solution. So this, the original string, if we didn't use Huffman and you a fixed 2-bit code for each letter. Yes. The frequency is no longer equal. The Huffman algorithm rebalances tree to ensure the most common characters get to prime real estate. 1 and P. A BBC. Try some challenge string. Mississippi. Which letter do you think will get a 2-bit code? And which one will likely end up with a 50? Okay, they give some example, but still don't understand what does it do. This is an example of a Huffman tree. And 36 characters. So assuming characters 8 by 288. So with this scheme, we get it down to 135. Let me check 1 second. So it looks like the first thing they'll do is there a leak code for this? Huffman coding. I knew it. Yep. Huffman coding. We can try to do this. Yeah. Shannon entropy. Mm. Basic technique. Technique work by creating a binary chip node. This can be stored in a regular array. Okay. So we create an array. And that can be either a leaf node or an internal node. A dead, that seated, a bad babe, a bearded ABC, whatever. Step 2 to 6, the letters are sorted by increasing frequency. And the least frequent to each step are combined and reinserted into the list. The final tree in step 6 are traverse. So let's look at this example. C appeared twice. C. B appears 6 times. 1, 2, 3, 4, 5, 6. So we basically create we for sure need to create a frequency. Somehow CB become 8, one of which C is 2, B 6. Select 3. So it look like from this scheme, the two lowest frequency have the parent with it, and then the next frequency we pick up, so 8 and 7 dB right here, right? And we continue the process. So now 15 gonna pick, what does it pick? 11, 7 and 8 we got ECB. 15 and E is 7, CB 8 is normal. Then somehow it picked, no, what happened to D here? Okay. just put it here, and then because it's greater than this, right? But isn't this greater than that? Look like it group every to small it become this, and then it picked 7 become 15. Okay, it always pick the two smallest. Let's make a tree. Okay, so this will be 10 10, good, and 20, right? 20 here, so 11 and 15. 11 and 15 become 26, so 20 and 26. Then finally we got the final tree, which is this one, 0 0 0 1. So this string become this string, right? So in other words, if we Python binary string to hex, so we do this example is anything, we will do hex up, integer up, right? So this is the how it becomes. So the original string is input equal, let's say we have this, the output now become right. So given the string up input 46 and the length of output is 31, we save a little bit, right? So if we don't do hex, we have we do, right? So output become like that. So 31, 35. So if we do, we save like 9 space. So yeah, so we first have to chunk the input into every characters, count the frequency, take every minimum frequency, pop them. So it's like this is like a heap, minimum heap, and we build this tree, right? And finally become this. So yeah, the letters are sorted by increasing frequency. Yep. The least frequent two of each step are combined and inserted into the list. A partial tree is constructed. Final tree in step 6. It travels to generate a dictionary in step 7. Okay, step 7 here. Oh, so this is the parent. Okay. E and then yep. So this is like you keep constructing a parent of this as if it's not apparent enough. Okay. And then what else? Step 8, use it to encode the message. Okay. So you have check Twitch. Stuff around. Okay. So you ended up with these is the parent to all this stuff. Go D, go down here. And ECB, okay. Okay. Let's read this one more time. Initially, all node are leaf node, which contains symbol itself. The weight bit 0 represent the following left child, and bit 1 represent the right child. Also, that's what it means. 0 is left, 1 is right. The finished tree has up to n leaf node and n minus 1 internal node. Okay, so internal node is basically parent node. The weight of the new node is set to the sum of the weight. Yep. So this is basically just 2 plus 6. Yep. I think my intuition is correct. You have to have a mean heap. Which mean that whenever you loop through all of these characters, gonna be n log n, something like that. It's a new node. Okay. Yep, it's n log n. Yeah. Remaining node is the root node. The tree is complete. pinging me? Big Tech thinks smart glass will be the first major piece of AI hardware. Okay, whatever. Oh, they can cut out to ON. If the symbols are sorted by probability, there is the linear time method to create half-tree using 2Q. The first one contains the initial weight. We will not try to be smart yet. Just do this, it's fine. What is this? Okay, so after the Huffman tree, which is basically the step 1 to 6 here, trees generated. Which map the symbol to binary code as follow. Statistical node set to the root. If the node is not a leaf node, label the edge to the left side at 0, the edge to the right at 1. Okay, so you start with A. Yeah. I don't understand how they get the last one here. Generally speaking, the process of decompression is simply a matter of translating the stream of prefix code to individual byte value. So maybe we also need another endpoint. Yeah. This is the node. Today is 0130. We added a section for so basically for this we have all of them. But oh man, a long time to edit. Okay, so this could be another surface where we also have the same thing. Decompress the URL. Description. Pretty much the same now. So we can do this. Then decompress. What is canonical encoding? So this is like the frequency. Let me look. So they're saying somehow we need to pass like a prefix the frequency table over. But does that mean we also need to store the frequency? In the table itself? me do some bathroom break. Okay. We are back. Normal Huffman coding assigns very long code to every symbol in the alphabet. So A, these numbers. Except the existing course. The bit length stayed the same by code word length, and secondly by the alphabetical value of the letters. How do they get from here to here? Was that because 0 first, then 11? Yeah. and see stuff. Each of the existing code I replace with a new one of the same length using the following algorithm. The first symbol in the list get assigned a code word which is same length as symbol original code word but all zero. So B0. What is the benefit here? Mm. Two-thirds of the constraint not known, only the number bit for X simple. So 2133. BACD. So one. What is A? Who's sending me all this stuff? To really study, you really need to just turn off the phone. Okay. We'll think about this later. Huffman coding steps. Yeah, this I understand. So this is the heap. Yeah, we know this. Mm. For each non-leaf node, assign 0 to the left, 1 to the right. 0 left, 1 right. Okay. Oh, this is how you get the 0 one. Okay. It's 2-bit, 3-bit, 0, 1-bit, 2-bit, 15, 28. You send over a number of characters here in the frequency. I don't want to see the code. Just give me example, bro. Who's sending me stuff? Let's watch some video as well. This one. How do we show? Let's do. This is background music. Pause the music for a little bit. Let's go this browser and we paste the music here. Interact. Who else keeps sending me all this stuff for what? Property.
B, A, D.
Why does no
And
music?
if I were going to code that in ASCII, that's 1, 2, 3, 4, 5, 6.
Hold on. Why
Let's get
there's
some
no
text that
sound?
we're going to code up. So A, B, C.
How do you make sure that this one has sound? Okay. One second. Technical difficulty.
Let's get some text that we're going to code up. So A, B, C, B, A,
Does this
D.
one have
And
sound?
if I were going to code that in ASCII, that's 1, 2, 3, 4, 5, 6, 7. 7 characters. So if I were using 7-bit ASCII, that would be 49 bits that I would need. And if I were using 8-bit ASCII, that would be 56 bits.
Example.
So let's try this. The first thing we need to do is to make a frequency table. So I need to.
Okay, today we are going to talk about
Why
Huffman
is there no
coding.
sound?
Huffman coding at the end has a tree structure, and I will show it later. And main reasons why we use Huffman coding.
Why is there no sound? Does it even have sound here? It does, but if you funnel through the to this thing, it doesn't give me sound. Me 1 second.
Okay, today we are going to talk about Huffman coding. Huffman coding at the end has a tree.
OBS. Let's do this. OBS browser sort, no sound. Oh, do you have to do background music? Ah, I see. This is what we need. Turn this on. There we go. I think this should work now. What? Browser, let's do
structure, and I will show it later. Main goals and main reasons why we use Huffman coding is that we encode symbols that have some probabilities, and the underlying tree structure can give a very good possibility to do that. Then Huffman coding is an optimal scheme. Results are very close to the entropy. Huffman tree is very easy to build, and it has intuitive structure, and Huffman tree concept can be modified for upgrades. I will show 3 of them. The idea of Huffman coding is to give lower probability symbols longer code, and for bigger probability symbols shorter one. To do that, we're going to consequently merge 2 nodes with smallest probabilities on each step, and thus we will produce nodes which contain probabilities of some symbols, and we will move according to these probabilities through the tree and the acquire codes. I will build a tree now, and you will understand what I mean very good. I made first 3 steps of the algorithm. So first we merged I and T and has given them their cumulative probability. If we continue, we can merge R because it has the lowest probability and the merged node. Thus we acquire newly merged node. Now we're in a situation we have to merge R and this merged node, and the tree will become a little messy because they have the lowest probability.
I still
to
think
before.
this is very contrived, and I think we need better example. Let's try this again.
You want to file free? Hit it.
TurboTax, free edition only, roughly 37% of filers qualify. Simple form, 1040 returns only. Now this is taxes.
Let's get some text that we're going to code up. So AA, B, C, B, A, D. And if I were going to code that in ASCII, that's 1, 2, 3, 4, 5, 6, 7 characters. So if I were using 7-bit ASCII, that would be 49 bits that I would need. And if I were using 8-bit ASCII, that would be 56 bits. So let's try this. The first thing we need to do is to make a frequency table. So I need to count the frequency or the number of each letter. So like there's 1, 2, 3, letter A, etc. So let's count these. The next thing that I do, I need to write these out in order of frequency. On the left, the most frequent. So. And then starting with the least frequent ones,
Okay.
I join them to make a new node. Now 1 plus 1 is 2, so that's now a new node, and these things are what we're going to call leaf nodes.
B.
Now this 2 needs to now be inserted into this thing called a priority queue. And then we take the 2 with the lowest frequency,
4.
which is this B, which there's 2 of, and then there's 2. Add them together. 2 plus 2 is 4. And then, remember this is a priority queue. This 4 is greater than 3, so when we rewrite it, we're going to put it there. So this time around, we've got 4 here. We've got A with a frequency of 3. The frequency of 1. That's now our new priority queue. We need to join these two, so 4 plus 3 7.
Okay.
And now that's our new priority queue. There's only one item in the priority queue, so our algorithm says stop at this point. Now, this is a Huffman tree, and now on the left, by convention, on the left-hand
This is
side, it's going to
0
be
and 1,
binary
I
bit
see.
0. Right, it's going to be 1. And now, going back to this frequency table,
So can
so
you
those are the frequencies, and then
not, like, when you build this tree, make this 0 and 1 as well, or do you label them after?
we can write the Huffman codes here.
Okay.
So, let's take the letter A to start with. Well, the code for letter A is just 1. The code for letter B is going to be 0, 0.
We have
What you
to
might
go
notice is the
down
most
leaf
frequently
note.
occurring letter, which in this case was the letter A, because that had a frequency of 3, which is greater than the other ones. It's going to have a nice short code, and that's important. So now that we know the codes, we can encode this. So letter A is 1. So let's just rewrite this. So the letter A is 1. The letter A is 1. The letter B is going to be 0, 0. In Huffman coded bit patterns, there won't be any spaces, so let's just write it out now. So, no spaces in that, and you might be thinking, well, how on earth could then you decode that to work out what the original text was? Well, it's easy. So, 1 is going to be A. 1 is still A, and then we've got 0, 0. So 0, 0 is B. And then 0, 1, 0 is C. Which is exactly what we started off with originally. A, A, B, C, B, A, D.
Okay.
So, what do you think of Gravity Zone?
Do another example.
Hi and welcome to this video where I'm going to give you an example of how we can use Huffman encoding to compress this string of text, Big Bob bites bananas. Now, before we begin, we should just be aware that between each word here is a space, so we're going to have to encode that as well. Now, the first thing we need to do when we are looking at compressing this string of text is find the frequency of each character. And the goal of the Huffman tree is to find the shortest possible representation for the most frequently repeating parts of the text or the phrase that we are encoding. However, if something only comes up once or twice, like this E only appears once, we can get away with a fairly long representation for that because we're not going to be repeating it in our text very often. So we're going to need to look at, for each character, what is the frequency, and I've got that here. So I just went through each character as it was. So I looked at the B, there were 5 B's, 2 I's, there's 1 G, there were 3 spaces, then we've got 1 O, 1 T, 1 E, 2 S's, bites and bananas, 3 A's, all in bananas, and 2 N's, again also both in banana. And the total there is 21, and that's a good little sanity check. You add those up. If you get the same length as your string, then you know you haven't missed any. Okay, so now that we've got our character frequencies, we can start building up our Huffman tree. And this is how we do it. We start off, we look through this chart and we find the items with the lowest frequencies first. Okay, so G, O, T, and E all have the lowest frequencies. So we're going to write those at the bottom of our tree, and we're going to give ourselves plenty of space. We start bottom up. So start in the bottom right, and we're going to say we've got a G. And so that's fine, we can cross that off. And we've got an O. Okay. And we've got a T. and we've got an E.
Okay.
Okay, and what we do is we need to combine these into pairs. So starting at the right hand side, we build up pairs into a little tree. And what I mean by that is we connect them together and we work out their combined total. So in this case, the combined frequency of those two was 2. Okay, and then we go on to our next pair where the combined total is going to be also 2, because for each of these characters we had a frequency of 1. Now if I'd had an extra, let's say I had 5 characters all with a frequency of 1, I would just have that here, and I couldn't pair it with anything, so I'd just leave it for now. I would just wait, we'd come back to it, and you'll see an example of that in a minute. Okay, so I've done my lowest level of frequency, so I'm going to move on to my next level of frequencies, which are the I, which had 2, S and N, all of which had 2. Now I'm going to write these physically higher up in my little hierarchy in my tree. So these were all like the 1 levels, and now I'm going to put my 2 levels kind of here. So I'm going to start off with my I. Okay, so I've done my I. What else did I have? I had an S, and I had an N. Here's going to be our unpaired item, and again I do exactly the same thing, working sort of from the right hand side. I start pairing them. So S and I has a combined total of 4, and N I just have to leave there for now because I haven't got anything to pair it with. Okay, so let's go through and do the next level, and that's going to be my space and my A, which are both 3. So I'm going to work at sort of like my next level up. So let's see.
Bro.
Let's go with space. So I'm going to put space here, and that's that one. And A. Okay, so that's my A gone. And again, working from the right hand side, I need to do some pairing. Well, this N is still unpaired, so we're going to pair the N and the space. The combined total for that is going to be, N was 2, space is 3, so it's going to be 5.
Pair the,
and the A,
the one with the pair
4
we just
into my diagram. Now we just go right back to the right hand side again, and we 5, which is characters. Right branch. All we do is every left branch we're going to label 0. So all of these are left branches where I go to the left from a
So
node.
basically, after we have
And all of my
the tree, we have to traverse them to figure out the code for each. So like B here 00 and whatever, right?
right branches I'm going to label 1. So that's all the way down the right. I've also got a right branch here, I've got a right branch here, a right branch here, and a right branch here.
After this, we will have a dictionary.
Okay. And from this tree, I can now get an encoding for every one of these characters.
Make sense?
So let's write that up maybe at the top. So let's go for character and encoding. Okay, and let's start here on the right hand side. So for the character B, our encoding, we start at the root. This is our root. And we just work down the path that gets us to the character we're interested in. So for the B, it was 0, 0. So the binary encoding is going to be 0, 0. Okay? Then the A was 0, 1. Okay? Then the next one we had was SP, which I went 1. I had to go to the right, so 1, 0, 0. So for SP
I'm
or
more
space,
interested
it
in
is
the
1.
decoding when you figure out the thing though.
0, 0 for B. Big 1, 1, 0, 1. G 1, 1, 1, 1, 1. Space 1, 0, 0. And then Bob, and so on. I'm going to complete this.
Okay.
Okay, and there is our encoding. So that's my B-I-G space B-O-B space Big Bob.
Feels like when we send this encoding over to our URL shortener, we probably from the pairing here we know the letter, right? So like we send over B, it become whatever. So in the shortener, what we can do is we can because the okay, let's finish this and then we'll talk more about this.
BITES space bytes BANANAS bananas. Okay, that's the encoding. So let's just look at how many characters, or sorry, how many bits we've used to encode that. 67. 67 bits to encode our message. Now, if we think about using 7-bit ASCII, our original message had 21 characters, if you remember. So if we had 21 times 7 bits per character, if we're assuming basic ASCII, that would be 147 bits for the original, but only 67 bits compressed. As you can see, that's a significant reduction of about 45% of the original size. Now, it's not quite as simple as that, because in reality, we have to also transmit with our encoded compressed data, we have to encode our dictionary as well. So we're obviously going to need a byte for every character we send, because we need to know what it translates to at the other end, plus the variable number of bits for each byte. So all of that data needs to be sent along with our encoded message.
Yeah, that's what I thought too.
And that can actually result in quite a significant increase, especially if you've used lots of different letters and a not very long string. But if we have quite a long piece of text, and these don't have to be individual characters, this could be pairs of characters that come up quite often, like T and H, or C and H, and things like that. You can compress the pairs, or whole words potentially, and then you can compress those as these, in a much more efficient format, and you end up with a dictionary that is proportionally not that big compared to the message that's being sent, and that's where you get your greatest encoding benefits. Now we need to see how would we actually use this to decode a message. Okay, so here is my binary string that's been encoded using this Huffman tree, and we need to decode that into a message. And one of the first things you'll think is, I don't even know when a character starts and ends. There's no obvious way of knowing.
This guy's fixed my mind. Okay,
It's
tell me.
because they're not fixed bit widths. So it's not like we have 7 bits per character like we do in ASCII. We could have 2 bits for some characters, we could have 3 bits for other characters. So how on earth are we going to break this down into a meaningful string? Well, let's go through it and show how it works.
At QFC, quality inspires everything we do because food handled with care just tastes better.
You know, I've always found it strange. People really want to save money, but are so willing to toss their hard-earned coin into a 3-foot pool of disappointment.
I want to be rich.
You don't need to throw your money away.
It's actually surprisingly easy. All you need to do is you start at the beginning of your string and you go to your root and you just follow all the bits through until you hit a character. We call that a leaf. So let's start here. So I've got a 0. So if I go to my root and I go to 0, I get here. So I'm not at a character yet. But then I've got another 0,
Oh, you just
which gets me
traversed the
here.
tree.
And that does get me to a character. 0, 0 gets me to the B. So this 0, 0 is a B. So let's now try the next one. So I've got an I. Sorry, I've got a 1 even. 1, another 1, another 1, another 1, a 0. Ah, that's got me to a character. So that must be where I finish. And that's an O, and that's a Bob. So now let's start my next one. I start right back up to
Okay.
the top. And I'm on a 0. Got me here. That's an 1 and a 1. Which does make sense. because we know that Big Bob bites bananas. So there you go. That's how we can take a string of text, encode it into a Huffman tree, which we then use to build a dictionary. And from that dictionary, we can then encode any message we like, and we can decode from there as well.
Okay. We have a rough idea of how it works. So actually, on the back end, let's defer the implementation of Huffman code to next stream maybe, because I gotta go soon. So in our table here, given an input, it need to give an output. And I guess there's another table. Let's do there is right. So we would have output URL, to input URL, right? So the expire time is very subjective, because we do that mainly because we want to relax our storage, right? So we would do a Huffman code, right? We'll do the implementation in Python maybe next stream. So let's say so we need to talk about step 4 here, the deep dive. There's the question. Can we use like one table? So for the sake of that, because we don't want many right way. So today, before we talk about stuff, we just need one table for shorten and de-shorten, right? So the next question we wanna ask is, So then, like, what is the? I think the question that we should talk about is capacity planning, right? So if we store the table, what is the capacity planning? And another question we have is, how do let's talk about that in the scaling. Million up concurrent request. How do we handle that? We could do the Huffman coding in the front end and schedule a backend. So this is not actually not direct customer facing. So our service would look something like this. The user make request to our service. Let's call this Huffman code service, right? Which is have like a behind an API gateway. Let's just say, right? And in this, it would run a Huffman tree generation, and then we will queue to DDB database, queue to write to DDB backend, right? And the it's also, right, populate from cache, right? Populate to cache, right? And then if possible, right? So if it adds up to the DDB backend, then it would just go back to populate to cache. Also from cache, if the result is in the DB already, right? So something like that. So the first thing this thing actually check is sorry. Okay. Oh. So the first thing this Huffman code service should do is let's do this. Check if the input is in cache. Okay, if it is in cache and grab them. Right. Otherwise, run the Huffman code tree generation, and then and then populate to cache. Possible, right? Something like that. Okay. Okay. So this way, if it is not, if it hit the surface, if you didn't see that, then so there should be another service called like DDB writer or something. This would write, grab the message and write to table if item does not exist. Okay. So we already talked about caching. Right. So about partitioning. So this way we have cache and something like that. You to write the DDB backend, and then we have a DDB writer. If we do DynamoDB, we can actually utilize condition check feature. DynamoDB condition check. Conditional check exception. To avoid writing the same into the table, right? So this is what I have roughly. So you have like a endpoint which is basically exposed by the API gateway. It's just an endpoint. This will talk to the Huffman code service, which is basically saying that if this input already in cache, then grab them. If it is not in cache, then run the Huffman code, put them in cache, and queue to the DDB. Queue write the DDB. Then every day populate the cache or something. There's some daily TTL cache invalidation scheme we can try. So if it's not in cache, try to grab them in TDB, right? In table, right? If grab them from table return nothing, then we would have to run the Huffman tree and return to customer, right? Something like that. So let's see what, okay, how are we fair compared to Gemini. Okay, now we look at the answer that it gave. Custom alias and link expiration. Okay, fine. I work with that. The directions if it cannot go down. 100 million new URL per month. Okay, so we should talk about the cost here, right? When we do storage, right? So let's say with the skiing we have here, do we need to talk about cost? Should we? Or do we? Yeah, so we have the correct idea. Some sort of database has to do. Also, Gemini actually recommend us that we generate some unique 7 character key. Okay. I use Huffman coding. What is your scheme? Okay, so Gemini think that Huffman code is overkill. Okay. Gemini thinks that the Huffman code ring of mine is complex and recommends 2 other approaches. Right. What does it recommend? Base 62 encoding. Key generation stuff. What? Okay, so this is something that we should talk about. We should talk about how we get 3.5 trillion unique URLs. Basically 62 to 7. So basically we make a auto increment ID and convert that to base 62, which is like half 0 to 9, A to Z, A to Z. Okay. So you would grab like one from here, one from here, one from here, whatever, right? Okay, it's a good idea. The second approach is oh, that's smart. So key generation service to regenerate or assign range of key to each server, right? So to scale, right? Because if using one table for auto increment, it become bottleneck. This is actually pretty legit idea. This could potentially be the solution. Yes. It's Justin Bieber problem. The schema will just have, I think I just need how about this? Okay. Gemini thinks our schema needs some tweak. Oh, okay. So, oh, okay. It doesn't care about the to save space. Okay, fine. my caching above is okay. The Justin Bieber problem. Yeah, I thought here that we can just have DynamoDB handle that. Okay. So in here we actually need, so Gemini thing that add read replica. I thought this is implemented by DynamoDB or something, so we probably should read the DynamoDB table next. Table DB paper next. Right. This is a good idea to talk about. Yes. Gemini thinks we should use Redis. We should read about Redis next. And LRU, sorry. Strategy. Compared to Gemini, I do not think about analytics at all, which is actually valid, because the machine learning team wanting to have data track all the time, so we should be thinking about that. But I do queue them, right? Hot partition fix. So scenario if a row is accessed more often than others. Oh, I did not talk about the load balancer at all. So basically, redirect always works. And then it would do schedule event to write to separate DDB DynamoDB table for analytics. So this is the redirect and analytic and not destroy at the same time in the event of outage, right? I also think that once we finish writing to the table, we can probably send event to replicate them in the backend through DynamoDB stream or such if we use DynamoDB. Right. So basically, Gemini architectures is client load balancer to web servers service, and this is Redis or TicoDB, and along with this there's an asynchronous process to Kafka to NoSQLDB for analytic, right? Final question for you. Cloud system is in London quick link, but other bay is in New York. That is 100 millisecond delay. How would you do latency for user cluster of pin? So we should add read replica or CDN to it, right? So that to reduce latency to customer. Okay, so this is my answer. Or have data clone to cast. So the question. Okay. Sheila explore glow. Yeah, that's what I thought. Okay, yes. Keep on exploring. Yeah, you can go very deep. This is the valid question. Okay, we do GeoDNS. Based on customer IP, give the address of geolocation data center nearest to said IP. Right? Then we do multi-region caching. We have regional Redis. The catch. How does London Reddit know what the URL will be useful or when the user get in a home region? So basically we would have global region replicate to regional region. Makes sense? That's a good idea. Oh, okay, so look into Edge redirect, allow the workers or AWS Lambda at Edge. Okay. Okay. To wrap up the system design interview, I might throw a curveball to see how I handle edge cases. How do we prevent people from sketching? How do we prevent people from scraping? Okay, so couple question. One is this. Number two is how do we prevent people from scraping our entire database by guessing every possible 7-character combination? My thinking is that we guessing every possible 7 characters combination. I actually don't know. Right? How do we stop user from creating URL that point to malware or phishing site? We can have a list that we pull or guarantee that it is the phishing site, and we pull from that into cache and avoid user from creating them in the first place. If a user wants to delete a link, how do we ensure it's clear from all global cache immediately. If the user wants to delete the link, this is my answer. So how do you make sure that it's clear from the cache immediately? Well, if the user delete a link, we would invalidate the cache from the current user cache, then propagate them to all the global caches. Depends how fast is the propagation delay with edge and or Cloudflare, right? That's what I think. So you basically fool the user saying that okay, this is actually clear. We can only clear it from the geolocation that it is serving the user right now. How do we prevent people from copying our entire data by guessing every possible 7 character? I think my answer is rate limit the potential or sensor hacker, right? Like if they trying to do that, then that gonna be like a lot of requests, right? So we ban the user if they trying that. Let's tackle all that curveball. Yep, I got the rate limit. Gemini suggests along with rate limit, you should do non-frequent. Use shuffle. Shuffle alphabet. Oh, Faisto Cipher. Okay, read about this. Yeah. Okay. Roughly agree. Suggesting something to think about. Refuse to shorten URL if zip browsing service found with a thread, right? So like Google save browsing or virus total, or like we can still shorten them, but cron job scan and hit the Google save browsing, mark them as unsafe as needed. Maybe we'll just like ban this local cache. Yep. So my answer is this. Yeah, so pretty much Gemini agrees somewhat. We can do active invalidation. Okay, active invalidation. Basically pops up delete message broadcast. Short UTL. Okay, so basically let the cache invalidate themselves by setting the lower universal spy time. Okay. Tombstone record. Mark the row as is deleted true. Okay. Nice. Pretty good. I think that's it for now. We will have to probably go soon. We will have to write the Substack of our last 3 stream or 2 stream, 3 stream, and then tomorrow we continue to maybe Huffman code implementation or something like that. That's it for now.